Good afternoon, everyone. I am Mr. Ish. You all know what an ellipse is. It's one of those more popular conic sections. In this video, we'll be looking at calculation of an area of an ellipse. We're going to do this in three ways, two of which will involve calculus. One of which is not going to involve calculus. It's just going to be the basic traditional technique. We will just call that using the formula of an ellipse. Area of an ellipse is equal to pi AB. We'll do it using that formula. You know, this is just like doing a basic arithmetic question right over here. Then we can do everything over here by means of the Riemann sums. We'll just abbreviate it. And then we can do a direct integration technique. Of course, these two are the calculus techniques right over here. Basic integral and direct integration. Area of ellipse should be an interesting video. You know, relatively, an ellipse is like an oblong circle. If you look at a standard ellipse directed horizontally, it might look something very much so like this. Focal point here, vertex here, minor axis endpoint, having a certain eccentricity, right? It's not circular, it's not a line, but it'll have a certain eccentricity. So let's look at an equation. Perhaps we can look at one of those more common or famous ellipse equations. We might have looked at it before, but of course we'll be looking at here everything in terms of area. What we can look at over here would be, how about 4x squared plus 9y squared is equal to 36. We look at this equation for our ellipse, and you know, you can get started right away by converting this into the dimensions or into the form that would give you the variety of items you need for these area calculations. If you divide everything by 36, so you can make everything equal to 1, you have x squared over 9, right? And then here you have y squared over 4 is equal to 1. A value over here, or you can think of it as this way: x squared over a squared, which is 3 squared, plus y squared over b squared, which is 2 squared, is equal to 1. So here clearly you know a, which represents your vertex value, is going to be 3, b is going to be 2, c is going to be the difference of these two in terms of their squares, and then the square root, because it's c squared is equal to a squared minus b squared. You know you'll get a root 5 over here. We have a center over here about the origin 0, 0. So the vertices over here, clearly, as you know, for horizontally directed, because here the a value is attached to the x, the a value, the larger with the x, therefore it's horizontally directed. Your vertices here would be plus and minus 3, 0. Your focal points here will be plus and minus root 5, 0. We know all of this because we've seen it. My minor axis endpoints would be 0, plus and minus 2. Eccentricity over here will be c over a, root 5 over 3. What do we really need over here for the area calculations? And in terms of how we're going to do, well, we need the basic equation form. We know we need that. We'll need these two right over here as well. If you look very carefully right here at the traditional form using the formula a equals pi ab, so we can calculate that right away. We have a, we have b, and we have pi. So our answer should be 6 pi. Using the traditional technique, which is the formula for an area of ellipse, we know we should get 6 pi. You can numerically calculate 6 times pi on your calculator, and you get 18.8495. So let's put that over here. It's going to be 18.84955592. And this represents a good accurate value for the area of this ellipse right over here. Let's look now in the remainder of the video at these two approaches, starting with the Riemann sums and then followed by the direct integration. You know we're dealing with this equation 4x squared plus 9y squared equals 36, the equation of a horizontally directed ellipse, and we have to determine the area of this ellipse. This time we're going to be doing the area calculation using Riemann sums. You know Riemann sums is basically a limit of sums. You're looking at everything in terms of Riemann rectangles. But a key aspect of this equation is this f of xi. You're dealing with some sort of a function. You know ellipse is not a function because when you draw it out and you run it through the vertical line test, a vertical line runs through the ellipse at more than one point. Therefore, it fails the vertical line test. You have to essentially convert that equation into a form of that representing a function. 9y squared is equal to 36 minus 4x squared. Y squared is equal to 36 minus 4x squared over 9. Y is equal to root of all of this, 4x squared over 9. If you look at this, and we can better simplify this, we can isolate a 4 from the numerator. You have 4 into 9 minus x squared divided by 9. But you see 4 and 9 is a perfect square. You can bring it out as 2 or 3 and you essentially just have 9 minus x squared. This right here represents now like an f of x version of that ellipse. This right here could represent a good equation form for f of xi, but the only problem with it is this: if you look at the graph of this, you know we're going from -3 to 3 in terms of our vertices, and we have a 2 over here and a -2 in terms of our minor axis endpoints. And the ellipse, the graph of this will look something like this. See, the graph of this will look like that. It'll only look like a half ellipse by virtue of this radical. But if you are trying to calculate the area of an entire ellipse, then you must compensate for this. And the only way you can do it is you can take this equation and multiply it by 2 at the end. So what happens over here in terms of our equation, it becomes 2 over 3 root 9 minus x squared. And then you know at the end of the calculation we can do it times 2. And I think a good idea over here is to calculate R8, meaning having an n value of 8. We'll have to calculate delta x. You know that. We know our intervals are -3 to 3. Right, -3 to 3, we'll do all of that interval. The determination, we'll basically do midpoints as sample values and feed them in here. We'll have this, and then at the end of this specific scenario, we have to do a times 2. But I'll erase it because it's not officially part of the formula, but we cannot forget to do the times 2. This right here, integral procedure, will only give us the area of this, but the times 2 will capture this part on the bottom, and we'll have the cumulative area of this entire ellipse over here. So this will represent our table of values. We have interval, we have the sample points, always using midpoints. We're not going to do any drawing over here. And our function f of xi, which will give us a length. We have to start by determining delta x. You know delta x is b minus a over n. What's b minus a? It's a big number, upper limit minus the lower limit. 3 minus 3 is 3 plus 3, which is 6 divided by 8. Which is what? 3 over 4. We know our n value is 8 simply because we're doing that. What are our intervals going to be? Our intervals are going to go from -3 to +3 by 0.75. So let's do it. -3 to minus 2.25. Then minus 2.25 to minus 1.5. Then minus 1.5 going up to minus 0.75. Then minus 0.75 to 0. 0 to 0.75. There will be a symmetry of values which will develop here, as you will see. 1.5 to 2.25, and the symmetry of values will develop by virtue of that square and that radical, and the fact that this will be similar to an even function with y-axis symmetry. And then 2.25 to 3. All we essentially have to do is determine these values, and these values individually will mimic those. We'll put in the midpoints of these values, and we'll start plugging in the values over here. Okay, now you see from the interval over here, I've determined the midpoints and I've put them here. Minus 2.625, positive 2.625, and correspondingly these minus and positives. 1.875, 1.125, and 0.375. Now we have to individually plug in these numbers, looking only here at the top 4, because these will mimic the results over there, and plug them in over here. If we want, at the end we can multiply by 2, or we can reserve that times 2 for this formula right over here, get our value and multiply it by 2. We can do that. I'll plug in all of these values over here, and then you can see the laid out values. I'm going to take 2.625 and plug it right here in place of x. I'll do 9 minus 2.625 negative square, and then root of that and multiply by 2 or 3, and I'll correspondingly do the same for all of these. Alright, now what you have before you are the values, f of xi values. Each of these individual xi values, sample midpoint values, placed into that function 2 over 3 root 9 minus x squared. I haven't done that final multiplying by 2. I'll reserve that for the end. But you can see there's symmetry. These two values are the same. These are the same. These are the same. And these are the same. 0.968, 1.56, 1.85, 1.98. And you can see onwards. You know, in terms of the accuracy of our area for this ellipse, right over here, the very first method using that area formula and then the very last method using direct integration will be the accurate values. This Riemann sum will be a good approximation. Using midpoint will have a good approximation. So what do we have to do now? Since we've determined the f of xi and we have 0.75 as our delta x, we have everything we need. All we have to do is the cumulative sum of all of this, which represents the cumulative lengths. We'll multiply by delta x and we'll multiply by times 2. The only reason why we have this extra times 2 is, if you remember, our graph of this function represented only a half ellipse, the top portion of the ellipse. The lower portion of the ellipse was lost by means of that radical, and that times 2 just goes in to compensate for that loss. I'm going to plug in the value right over here on the bottom. We'll do the cumulative sum over here, multiply by 0.75, and finally multiply by times 2. And let's post that answer. So when I do so, I get the value over here 19.10357. It can be, of course, not an accurate answer because we have approximations come into play when you're doing the Riemann sums. And you see that when you compare with the first two, you know, we've already gotten pi AB to be the formula, which was pi times 6, and we know that was 6 times pi, it was 18.8, and I wrote the rest earlier, and I won't write too much over here. 18.8495. Here we're getting a slightly higher number, but that's fine. We can be either off above it or either off from below it, but we will be definitely off simply because we have an assumption here of 8 rectangles, Riemann rectangles. Had you drawn an infinite number of those Riemann rectangles and calculate infinitely the areas of those infinite cumulative rectangles, you would have come up to the true value, which will be 18.8495, and the remainder digits after that. What remains now is to look at the same area of this ellipse but using direct integration techniques. Now we examine the area of that ellipse right there on the top through integral calculus technique. You know the ellipse has been converted into this form. I don't want it to look like a circle because it's not a semicircle, into that form. Vertex here was -3, 0, 3, 0, minor axis endpoint here was 0, 2, and we were looking at this area in terms of that equation which has been arrowed. Simply because we've lost this portion over here on the bottom, we have that times 2. And we know our integral will be from -3 to 3. But if we're looking at the area over here from -3 to 3 for that function, 2 over 3 can be pushed outside. Root 9 minus x squared dx is our integral. I'm not going to worry about that 2 until the very end. You see this 2 over here, we're not going to bring it in until the very end. I want to use the fact that this represents an even function in terms of its appearance. Look at it. It'll be an even function. It'll easily pass this test. F of x will equal f of minus x. It'll easily do that. So we have symmetry here about the y-axis. We can therefore condense our interval, because at the end we still have to do direct integration over here. We can view everything as this. Area will equal 4 over 3 from 0 to 3. Root 9 minus x squared dx. Why is this 4 over 3? Because if you're going to do from 0 to 3, you can bring in that 2. That 2 multiplies with this 2 over 3 makes it 4 over 3. So this right here will represent our integral, which will represent the area of this part right over here. And then we'll multiply it by 2 to capture this part right here at the bottom. So let's integrate this. We're going to have to use trigonometric integration procedure over here because I think that will be a good reliable method. And this video is being presented, as you know, before you know many of these procedures, but that's fine. It's giving an indication of what lies before us in terms of what we will learn and what we can do with those integral techniques that we are about to learn in the coming weeks. When you look over here, you think about a trigonometric substitution technique and you will learn all of this. A is equal to 3, then x is equal to 3 sine theta. Dx is equal to 3 cosine theta. And in direct integration, once you start making substitution, these intervals over here, upper and lower limits, change accordingly. Theta 1 must equal, you have to take this equation over here and solve it with regards to these x values, which are 0 and 3. If 3 sine theta is equal to 0, sine theta is equal to 0, theta is equal to inverse of that 0, which is just 0. And theta 2 value will change too. If 3 sine theta is equal to 3, sine theta is equal to 1, inverse of sine of that 1 in terms of theta is going to give you pi over 2. So now all of a sudden our intervals have become from 0 to pi over 2. You see how we've converted these numbers into these type of intervals. The domain has been changed in terms of format, and we have 9 minus 9 sine squared theta, and dx here is 3 cosine theta, 3 cosine theta, d theta. Let's not forget this d theta over here. This 3 and this 3 can cancel out. So what we end up having is 4 from pi over 2, 0. Based on that trigonometric identity, sine square x plus cosine square x equals 1. You can isolate here 9 and you can do 1 minus sine squared theta. So you're essentially looking at 9 cosine squared theta, and then you have this cosine theta sitting outside. When you simplify this, the square root of 9 cosine squared theta is just 3 cosine theta. That 3 cosine theta multiplies with this cosine theta and you get 3 cosine squared theta. 3 cosine squared theta, but this 3 can multiply with this 4 and give you a 12 right out here on the top as a coefficient. So essentially we've boiled all of this expression down into this, and at the end we still have to do that multiplying by 2 at the end. you can use a power reducing formula. Cosine squared theta is equal to 1 plus cosine 2 theta over 2. So this cosine squared theta gets replaced by this 1 plus cosine 2 theta over 2, which some books call half angle formulas. I call it a power reducing because I'm reducing a power of exponent 2 into a power of exponent 1. This 12 and this 2 can simplify to bring a 6 back over here. We can separate everything across integrals. We have 6, 0, pi over 2 d theta, and across the positive sign we're splitting times 6, 0, pi over 2 cosine 2 theta d theta. We can do the integration over here. I did a lot of steps skipping over here simply because of space limitation. The integral of this d theta, as you will learn, will be just theta, and you'll have a 6 sitting outside with a pi over 2 upper and a 0 lower limit, plus you have to do a substitution technique over here, which you will learn. If u is equal to 2 theta, then du is equal to 2 d theta, and d theta is equal to du over 2. But this substitution will affect these intervals. If u is equal to 2 theta, u1, which you will learn, is equal to 0, and u2 is equal to pi. So this part over here becomes a new set of intervals 0 to pi, and you end up having a cosine u du over 2. But don't worry, I've not forgotten anything over here. I have this 6 sitting outside here, and we're going to divide it by this 2 which came through. This, see, over 2, this over 2. What we end up getting is 6 theta over the interval pi over 2 and 0 plus 3 from interval pi 0 cosine u du. We have to integrate this still. The integral of cosine u is a sine u. So let's bring in the sine u. The integral of cosine u is a sine u with the 3 sitting outside. 3 sine u from interval pi to 0. Sine of 180 minus sine of 0 is 0. 0 multiplies by this 3 and it cancels it all and makes it 0. Essentially this entire expression boils down to 6 theta over the interval pi over 2 and 0. So you end up having just 6 times pi over 2, which is just 3 pi. But let's not forget this. This becomes 3 pi times I2 and 6 pi. So the area of this ellipse, this entire ellipse, is 6 pi, but the area of just this top portion is a 3 pi, as you see right here, 3 pi. But you have to multiply by 2 because we're looking at the area of a whole ellipse, not a semi-ellipse. And then think back to the very first way we did the same question. Area of an ellipse was equal to pi AB. Pi times 3 times b, 2, which is a 6 pi. And you know we have that 6 pi. We numerically calculated 6 pi to be the accurate value of the area of this ellipse. 6 times pi on your calculator is 18.84955592. But via the Riemann Sums technique we got something in terms of 19 point onwards. And that, you know, was an approximated value anyways. This right here is the accurate area of this ellipse, and this right here is an accurate area. The Riemann Sums just provides you a good approximation. But here you have it, that the integral has leaded you to a good value in terms of the area, a true value of the area of this ellipse. So now you've seen how ellipses can have their areas determined. You can use a basic formula of an ellipse. You can use Riemann rectangles and the Riemann Sums technique, or you can use direct integration techniques, which perhaps is a superior technique. But when in doubt, when able, you always go with the simplest technique because it's time saving and it's proven. If you didn't know this, if you didn't know that the area of the ellipse was pi AB, then you can do all of this and still come up at the same answer. That right there is a good value of integral calculus, that you can do many things that you normally couldn't, and you can do many things that you normally can now just by learning basic integral calculus techniques. That'll be it for this video. I hope you enjoyed watching this video. Thank you for watching. Have a nice day.